Hello, welcome to the ENS webinar today. Today we will learn how shielding fuel assemblies will ensure plant life extension. Our speakers are Malin Löwe from Vattenfall Nuclear Fuel. Malin is Key Account Manager responsible for the fuel deliveries to Ringhals, and Lars Ackermann from Framatome. Lars is Project Manager in the Fuel Division of Fluent Topics. We will have a presentation about 40 minutes, and then there will be time for questions and answers. Lars, I will give you now the floor and to your presentation.
Thank you very much, and thank you for the chance to speak today in the ENS webinar. I will give you a talk which I have given 2 weeks ago at the Top Fuel in Seattle, and the topic is about the Framatome shielding fuel assemblies which ensure plant lifetime extension. And you have today not only the chance to hear this talk not being in Seattle, you also have 2 added values more. So I very welcome my colleague from Vattenfall, Malin Löwe. She will present the operational experience feedback direct from customer view. And the other added value for you is that we have more than double time to go much more deeper in details and show you the results of the shielding fuel assemblies. But first of all, I want to show that this presentation is in general a common presentation of Vattenfall and Framatome with already 8 authors. And I want to thank everybody for his contribution. And I also want to thank everybody behind the scenes which organized all these things, especially in this case, the ENS webinar. So what we are speaking today. First of all, Malin will give us an introduction about the Ringhals 3 nuclear power plant in which the shielding fuel assemblies are applied. Then I will speak about the different designs of the shielding fuel assemblies and their effect on the neutron fluence. And then Malin will speak about the operation experience feedback. So Malin, I would hand over to you to introduce Ringhals 3.
Okay, thank you, Lars, for this introduction, and thank you for taking me into this presentation. I heard you in Seattle and you performed it very well there, and so I'm honored that you will take me in to have this presentation together with you today. And about Ringhals 3, this is a Vattenfall-owned reactor situated on the west coast of Sweden, and it's about 60 kilometers south from Gothenburg, the second largest city in Sweden. And it's a so-called 3-low pressurized water reactor and was designed by Westinghouse. And as some curious facts, it's that the reactor pressure vessel were built in Sweden by Uddcomb Combustion Engineering. And the reactor was taken into commercial operation in the 9 September in 1981. And just a few years later, Ringhals 4 was taken into operation. It was supposed to take into operation a bit earlier, but at that time there were very few skilled persons to work in the plant, so they couldn't start as early as they wanted. That's also just some curious facts. So we are in a situation when we need to keep the competent people in our business as well to keep on going with the nuclear power. So the original rated power for Ringhals 3 was 950 megawatt electric power, and the thermal power was 2,775. And for the Ringhals 3 did a very large power uprate, as probably it's quite known. Was a very large project called the Great Project, and it was done in 2 parts actually, but the last part was done in 2008, and it was raised to approximately 10,070 megawatt electric power, and for it is meant approximately about 13% more power. So it was a very good part that contribute to the Sweden electric power. It also produces about 1/10 of all the electric power needed in Sweden per year. And the thermal power of Ringhals 3 is nowadays 2,992. But this power uprate, of course, implied several things, and amongst that is the increase of the neutron flux that was raised to 1 mega electron volt, and that's about 10%. It's a little bit more, but 10% is a good figure of azimuthal maximum, and it's at the height of the beltline weld. So the question for today's webinar is not this power uprate, but how is it possible to combine this lifetime extension that's we want to do in Sweden with the Ringhals 3, and also keep on going with this power uprated reactor. So please, Lars, go on and talk about that.
Yeah, well, it's a very good question. How can this be combined? So we already heard that the limiting position is the beltline valve W4, which is located 555 millimeter below the core midplane. So what can be done? First of all, we have to analyze where is the maximum neutron flux located. So it's on the periphery. You can see it here. And already in the beginning, there were inserted so-called neutron pads to reduce the neutron flux at this position. Well, it's not that much, but it was already in the design phase introduced. But the downcomer has limited space, so adding any additional neutron pads and plug this area, it's not possible. Larger modifications on the RPV is also not possible. So what we can do is to think about the fuel assemblies which are located on these peripheral positions. So these 12 fuel assemblies were replaced by so-called shielding fuel assemblies, which have a special design. So when you want to compare these things, it's difficult to use the real core design of the plant because you always have effects of the operation, which makes it difficult to compare the shielded design with the reference case. That's why for the investigation of the shielding factor, first of all, a lithium core was used. In this lithium core, it's clear it's always the same amount of fresh fuel assemblies going into reactor. Spent fuels go out of the reactor, and they're always positioned in the same way, so that you have the lithium core. And in this lithium core, you can now insert the shielding fuel assemblies and can compare the shielded case with the reference case. And by comparing this, you can get the shielding factor. So it's the ratio between the neutron flux of the unshielded case and the shielded case. So how was this analysis performed? First of all, it was a typical core design calculation with the core code to get a typical core design analysis. And then this data was transferred into an MCP model to perform the particle transport out to the RPV. And this picture you can see here is a cut view of the MCP model. And you see it's a very detailed model. So we have every pin by pin fuel assembly with 32 axial layers. So it's a lot of amount of data which is transferred from the core design to the MCP input, but it's all traceable because it has a direct line. And then the MCP model contains all relevant parts. You can see here some are named like the RPV, of course, the biological shield due to reflection back to the RPV. But also, if you look axial, you would see former plates. Okay, but what is the design of the shielding fuel assemblies? And well, in 2009, the first shielding fuel assemblies were introduced in Ringhals 3. And the design was a non-radial homogeneous design because it was made of 9 rows of 1% enriched uranium-235 fuel. You can see it here in the orange area, and 0.2% enriched 235 uranium for these 5 yellow rows in this area. And then on the outer surface, you have 3 rows with steel rods. Additionally, due to the fact that we are on the peripheral position where you have no control rods located, the guide tube positions were also put in solid steel bars to increase the shielding factor. So you can see this design is not rotational symmetric, but it's axially absolute homogeneous. The rest of the fuel assembly, the shielding fuel assembly, does not look different to the ordinary fuel assembly. So handling and operation is not influenced by the design itself. It's only a part of the neutronic and the heat production. So this shielding fuel assembly design was used until 2015. In the outage 2015, the advanced shielding fuel assembly design was introduced. And this is a totally new design. It's a split of the top part and the bottom part. You can see it here very good in the three-dimensional picture. On the bottom part, you have the shielding. And in this area, every pin position has a solid steel bar. And of course, the guide tubes are still made of solid steel. But in the top part, there it looks more like an ordinary fuel assembly. Only the guide tubes, the steel bars are still there. But on the pin size, you can see that every pin has an original enrichment of 1% uranium-235. And this means that in the top part, the shielding fuel assembly acts as an ordinary fuel assembly. It's rotational symmetric, so it gives you more possibility to position this shielding fuel assembly on the core. You can rotate it, you can put it on an isoperipheric position, and that makes it more flexible to use it and to have adequate burn up over time. But what is the effect when we now introduce these shielding fuel assemblies? So let's first look at the unshielded case. You see here the red curve shows the neutron flux for 1/8 of the core along the RPV, the height of the beltline weld W4. And well, as I already said, the maximum is on the peripheral position, so at 0 degree. And then it's decreasing, that's for sure, because it comes then to the edge element and goes further to the 45-degree position. So if you put in the shielding fuel assembly design, you put this maximum downwards so that this absolute maximum is now only a local maximum with even a slow drop and going up to a maximum at approximately 20 degree. And then it goes until 45 degree back to the already known values of the flux. This ratio at 0 degree results in a shielding factor of 2.3. So it can be said that the shielding factor of 2 already doubles the remaining lifetime. But by introducing the advanced shielding fuel assemblies, you can see the flux at the 0 degree is dropping to an absolute minimum with a slow increase now until 7-8 degree, and then comes up to a new maximum at about 23-24 degree. And this is very good, a very good shielding factor. So you also can look at this on the axial profile. So for sure, if you only use the shielding fuel assembly design, which has axially a homogeneous design, then you have a nearly constant shielding factor of this 2.3. So it's a constant shielding factor over the whole height. That sounds plausible. But with the advanced shielding fuel assembly design, you can see that in the top part, the shielding factor is principally negligible. Well, this is what we want. We want to have an ordinary fuel assembly in this area. But then when we come to the core midplane, where it's the overlap from top part to bottom part, so from the fuel part to the shielded part in the shielding fuel assembly, then you see a strong increase, a strong gradient of the shielding factor, which reaches here a plateau, and this plateau is reached just at the beltline weld. So the shielding factor is very good reached at this critical position we want to protect. If you would look at this point on the flux map, you could even see the former plates coming from the MCP calculations. So this shows that these results are very high resolution results and show a very good design proposal for the fuel assemblies. And Malin will now speak about the feedback from operation experience.
Okay, thank you. And of course, everybody understands that all this demands a very thorough dosimetry analysis and to follow up for see if all of this is actually true about what the shielding factor is, and so that we are really protecting the weld in the way that the shielding assembly is said to be. And for this, Ringhouse has set up a comprehensive series of neutron dosimetry measurements, and it was and consisting of a surveillance capsules, and it was reactor pressure vessel cladding samples and an ex-vessel neutron dosimetry, and all this has been analyzed and compared to the results of MCNP calculation, a three-dimensional cycle-specific neutron transport calculation. And this has been performed for Ringhouse 3 as well as previously for Ringhouse 4 as well. And all of this has shown a comparison that is very excellent agreement between the calculations and the measurements. So the shielding factors that have been measured and was prognosis was actually also the facts that came out from the shielding assemblies. And to verify the actual flux reduction that's been achieved and to provide for this comprehensive monitoring of the RPV neutron exposure, the ex-vessel neutron dosimetry was introduced into Ringhouse 4 and also into Ringhouse 3 in 2008, before the first shielding assemblies, just to have the possibility to see before and after the introduction of the shielding assemblies. And this was placed in the cavity right outside the RPV, and it could then measure all the full height of the shielding assemblies and the whole reactor core as well. So then this dosimeter was removed and it was analyzed and replaced the next outage in 2009, so that it could be taken out again and to verify that the actual measurement was the correct one. And then we have the ex-vessel neutron dosimetry, and the installation is just some small aluminium dosimeter capsules that is connected and supported by a stainless steel bead chain. And the capsules are located in the annular space between the reactor vessel reflective insulation and the concrete primary biological shield at the azimuthal angles of, as you saw in the picture, I think in 0, 15, 13, and 45 in like a single octant. And the capsules are located actually at the belt-lined weld location, and is of course at the flux peak that this should be capturing the whole flux that is in the reactor. And then we also have the reactor pressure vessel cladding samples, as can be used for this retrospective neutron dosimeter, and it has been established in the world in the VVE reactors, and after that it could be used, this technique, also in Ringhouse. And this sort of clad sampling was a very unique set of equipment, and it also performed a very good agreement with the calculation that was done. So in the end, the uncertainty level between the calculated and the measured activity was within 13%. And by this, we can be very sure of that the shielding factor is actually protecting the weld in the way it should do. So the embrittlement of the weld will not escalate in the same tempo as it did in the beginning, as you can see in the diagram to the right of the text. As you can see, if we hadn't installed these shielding assemblies, the first generation as we also call them, and the advanced shielding fuel assembly, the second generation as we also call them here, you can see it really have a very sharp curve that is flattening out, and by this is also making it possible to increase the whole lifetime and until the 50 effective full power years. So the measurements that I talked about before were made at where you can see the different black hours in the picture, and it was performed at the cycle 26, 27, 32, and 33. So this is for the first two, it was performed also for Ringhals 4. So we have actually two reactors that we can compare with, and they show exactly the same results for these two, for the shielding assembly in the first generation. So it was performed in, the first one was performed in 2008 and 2009. And for the operation experience as well, if we take the next slide, is that the total heat generation is of course reduced, and it's reduced about 4% due to the replacement of the fuel in the shielding assemblies. It's replaced with the steel, and this implies that the F delta H and the FQ in the calculation must be reduced by the same amount, that is 4%. This of course puts some requirements when you're doing the core designs, and you get a bit less flexibility in the core designs. That means that it's a bit harder to make core designs that fulfills all the requirements regarding the reload safety evaluation, as well as the requirements we have for what kind of operation and cycle length that we want to achieve each and every year. But until now, we have always been able to fulfill all these requirements, as well as the cycle length that's the requirements from Ringhals. But we can also see that it's in every cycle there is a top peak power profiles in all the closest fuel assemblies, and this needs to taken care of when you're doing the core design, so that you know that the next time when you shuffle, you should put them in certain positions that makes this level out. And this is no problem. We have all the equipment for monitor all this, and also an increase in the actual offset in the whole core, but it's within the limits of the actual offsets in each cycle. And we had until now 6 core with the shielding assemblies and 4 cores, core designs with the advanced shielding assemblies, the second generation. And as I said, there has not been any significant impact on the fuel economics or at all on the safety requirements, but the calculations around it is also very thorough, and sometimes you have to retry more when you do the core designs than you have to do when you working without the shielding assemblies. So in total, it has been a very good experience that you can have this very advanced fuel assemblies that's making the core, the reactivity in the core less, but still you can keep all the requirements that you must for operation. So we also, of course, had done the visual inspections. We have done inspections on the shielding assembly, and also this is a very thorough program for and follow up that Framatome has been doing together with Ringhals. All the fuel shielding assemblies has been inspected in different times, and they have been concentrating especially on the fuel oxide thickness, as well as the hold down spring force. since there was in the beginning, in a way, the hold down spring force was not exactly in the way that was optimized. So after in 2014 and 15, it was performed on the shielding assembly, the generation 1, and there were detected some signs of deformation and cracks in the hold down spring leaves. And then it was stated that this was needed to be replaced, but as we shifted and replaced the first generation to the advanced shielding fuel assemblies, the generation 2, we didn't need to do this replacement with the top nozzle device that could be done by just replacing with a new set of advanced shielding fuel assemblies. But then, unfortunately, it was detected also in 2018 and this year that there were some signs of deformation and cracks in the spring leaves. So it is decided that it should be also replaced, but the new type of top nozzle has been optimized now, and there is going to be a project in springtime to replace them with the next type of top nozzle device. But in total, all the visual inspections have shown very good performance, especially when you come to rod bow. That is absolutely no rod bow or fuel assembly bow. And maybe some of you listeners have been hearing about that we have fuel bow in Ringhouse, but for the shielding fuel assemblies, there is no fuel bow at all. And they're also working as some sort, you could say, stabilizers at the end of the core, at the core periphery. So in this way, they're also working in a good way for the core. There are also the steel guide bars have shown very little increased creep resistance and resistance to deformation, and all this regarding the inspection that has shown very little impact on any of the fuel handling operations. But I do remember that when the first time when the shielding assemblies, this is also curiosity at now, there was with the gripping handling, there was some a bit of a trouble that when they were going to put them in, but it was not exactly fit for the shielding assemblies. But the Framatome immediately came up with a solution for that and performed it in an exemplary way. So there were no delays in when we were going to install them for the first time in 2009. So this is a long time ago, and it didn't happen again. But after that, we know how to put them into the core. So for everything about the visual inspection, there is continued the inspection of the fuel assemblies each cycle and after in each outage, and there has been no problem with the outage inspections and has been performed in due time, and all performance regarding the corrosion and fuel rod diameter and all this has been very good and in a comparable way with other fuel assemblies. So now we come to the summary for this whole webinar, and the shielding fuel assemblies, the first generation, was introduced and has been working in Ringhouse since 2009 and until 2015, and it has been validated by thorough analysis with a shielding factor of 2.3. But since we needed a higher shielding factor for the Ringhouse 3, then the advanced design was introduced in 2015, and it has also been validated in the same manner as for Ringhouse 3 and 4 before with the ringhouse with the fuel assemblies of the first generation, and for this the shielding factor is 7.5, and all the operation experience is comparable to the standard fuel that we had have in core and ringhouse, and it from all the vendors, and it's about the dimensional stability and for corrosion and the fuel rod growth. It has been only small marginally fuel rod growth, and as I said before here, the stability is, you must say, it's even more stable than the other fuel assemblies, of course, due to the replacement with steel bars. So as you can see in the picture to the right as well, that it has the lifetime and operating time can be extended to the 50 years that we have been talking about, that we want and need to do in Sweden. So with the shielding assembly, this will be possible.
Yes, thank you, Malin, for this summary. And I think it's a very good feedback from you with the customer view and giving more insight than it's possible for us. And it was very interesting. And yes, of course, there might be sometimes some problems, but we are always working on continuing and improving our designs. And yeah, you already have spoken about this picture here in the summary. I think it's a very good overview showing that these strong fluence happened to ringheist in the first operating years. Now, if you double this operation time, you have only an increase of 24% or even less. So it's showing that the shielding fuel assembly solution is a very good one. And well, when we analyze the problem first, we can develop a customer-specific designs to meet all the safety and the economic targets. And I think it's a very good result and a very good history we already have with the shielding fuel assemblies with you together. And well, I want to thank you for your feedback and your support in this presentation. And I also want to thank Kirsten for organizing this ENS webinar and all of the attendees for listening. And I would say now it's time for questions.
Yes, thank you very much, Malin and Lars. Yes, actually, we have time for questions. What I will do, I will first maybe put the cameras on so that I can see you, and then so what we'll do is the attendees, you can raise hands. You can do two things. Either you raise hands with the little raise hand button, and then I will unmute you and you can ask your questions and interact with the speakers, or you type a question into the question bar on your screen. So are there any questions? Well, if not, I can start with a question. So does shielding fuel assemblies affect on X-core detectors, and how is this effect taken into account?
Well, there might be an effect on X-core detectors. This is something you can analyze in the MCMP calculations. And you also can analyze it in a four-dimensional way, so 3 times for the place and 1 for the time dimension, because especially if you're operating with long cycles, or maybe instead of 1 year, a 2-year cycle, then the core might change, and all this can be taken into account, and also the activity and the count rate of the detectors can be modeled, and effects on the X-cores can be investigated, and may adaptation of the design, which is necessary, can be done then based on that.
Okay, thank you very much.
Yeah, I could fill in a bit there because I spoke to Ringhouse about those, since they have also changed the detector system in Ringhouse during these years. So it's not the same that they used with the first generation with the shielding assemblies. So the X-core detector signals are not significantly influenced by the presence of the shielding fuel assemblies, since the location of the detectors are quite far from the positions that you know, the positions you saw in the picture before at 0 and 90 degrees. The X-core detector positions at 45 and 135 degrees. And the X-core detector's so-called field of sight basically covers the closest and the most peripheral assemblies, and therefore the contribution from the shielding fuel assemblies are not that significant. But as you say, there is some, and this is something that Ringhals is aware of and have been continuously looking into.
Okay, thank you very much. There's one question whether the presentation will be shared. Yes, actually all registered attendees to this webinar will automatically receive the recording of this webinar. So this is one question. And then I see that Timo Merisari is asking a question. Timo, I will unmute you. Maybe you want to ask your question? Hello,
okay,
Timo?
can you hear me?
Yes, we can hear you now.
Yes, thank you for the presentation. I was wondering, what is the lifetime of these new advanced shielding assemblies?
Well, it was designed to have a lifetime of 8 cycles, but in principle, it's a question how you want to enrich and how you want to operate it, so this can be customized.
Okay, thank you. Then if it's possible, I would also have another one.
Yes, please go ahead.
Did you
Sorry,
consider?
I didn't hear the question.
Did you consider SFAs made completely from steel rods without uranium?
Okay, this is a question for, I think, us. And yes, we did consider that. That was one of the first basic options that we looked into. But as you are fully aware of, that would mean that you take away much more of the reactivity of the core, and that would mean less production from the core. And so we wanted to have another solution that will not affect the core reactivity and the production of the Ringhals reactors. So then we started off this very large project to look into a design that would not take away that much of the core reactivity.
Thank you.
Okay, thank you. So there's also a question from Carlos Vasquez Rodriguez. I'm going to unmute you, Carlos. Maybe you present yourself because I cannot see where you're from. Hello, Carlos? Well, then Carlos, you want to ask your question? Okay, so then I will read his question. He's asking, have you thought to apply these solutions to other reactors designs, or is it specific and needed for this larger power up-rated reactors? Okay, now I see his microphone doesn't work.
Okay, so in principle, it's possible to deliver shielding fuel assemblies to every plant which has a problem. It might be a question if the shielding part is needed in the bottom area, so this has to be investigated. But in principle, it's not linked to the power uprate. It's only interesting that the power uprate was just before the introduction here in Ringhals. But in principle, if there are any problems, the fluence analysis can be done, and the optimized shielding fuel assemblies can be designed, or maybe even one of the existing solutions would be already sufficient.
Okay,
Yeah,
thank you.
because I can fill in that, as you said, it's not to the power uprate, but the power uprate, it put it more restraints on the Ringhals reactor, on the pressure vessel, because the weld brittlement was the problem for Ringhals. Both 3 and 4 was had this issue, but it's the status for Ringhals 4 is much better. So now it's not used in Ringhals 4 anymore, but for Ringhals 3 that has how the pressure vessel weld was made was in a bit different way than for the Ringhals 4. So when the power uprate came into action, it was put more restraints on how to operate the reactor, and therefore we needed to take this design of the shielding fuel assemblies is on the table.
Okay, thank you. So I have another question. Is it possible to apply higher enrichment in the fuel part of the shield assembly?
Yes, of course, it's possible to introduce higher enrichments. It only depends on the licensing in which it's possible to enrich in the plant, but it's comparable to the fuel assemblies already in the core. So it's in principle, from manufacturing point of view, it's not limited in that way.
Okay, thank you. MCNP models are very detailed. What experience in validation do you have?
Well, we use MCNP for a lot of fluence analysis, and we have over 100 samples, scrap samples, and so on, where we have measurements to check that. And as I said, they are that detailed that you can even see small effects like former blades and so on. So these measurements give us the validation that we are in the range of 10% deviation. So it's very good, and it's comparable with the results we have seen here in this presentation.
Okay, thank you. So, another question, is it possible to shield dedicated areas more central on non-periphery positions?
Yes, in principle, the design can be adapted to have shielding on the position where it's needed. So as I already answered the earlier question, if you have the problem in the top part instead of the bottom part, it would be the same way that then you have to analyze and to optimize the design for this purpose. But in principle, it's possible, yes.
I was just curious, was the question about if you wanted to shield something inside the core or another position at the periphery? I didn't really catch if it was just another position on the periphery. Of course, it's possible, but inside the core, they would put a lot of requirements for the core designs as well for how to calculate the core designs.
Okay.
Well, I could imagine that maybe it would not be the peripheral position, but maybe on a 45-degree, which is a little bit more difficult than, because then you are not in this rectangular way. But in principle, it's also possible to do it on that. So that's how I understood the question.
Okay.
Okay. So I might have one last question. Is it possible to have a 3-segmented shielding design?
Well, in principle, it's possible to have one. Our experience is with the 2-segmented, but it could be designed, yes.
Yeah. So, are there any other questions? Are there any other operators who are implementing the shielding fuel assemblies, or are you the leader of the fuel market?
Well, from my knowledge, it's Heist which used these shielding fuel assemblies, but there were already some plants, one in Germany, and I heard of in US, and there might be more. I'm not aware of that, which are using shieldings, but not shield assemblies with such a combination. We have it here.
Okay. Well, then I would like to thank you, both of you again, Lars and Marlene, and yeah, and then we'll end this webinar. I hope to see you all again on our next webinar on the 7th of November. Thank you very much.